Before we start your notes and examples, I'd like to go through a quick review of where the different formulas for triangles and the special quadrilaterals come from. I'll be looking at the area formulas. Here I have a virtual parallelogram. As you can see, I've got two bases that are parallel, and here's the height, and the two sides are congruent and parallel. Now, any parallelogram you're looking at can actually be cut up into three parts. If I drop the height from here to here and from here to here, the two corner pieces become right triangles, and they are congruent right triangles because the hypotenuse there and the hypotenuse are the same, and these two pieces here will also be the same, and the heights are the same, so they are congruent. Now, if I were to try to calculate the area for this, initially this could be intimidating, but the way we get the formula for the area of a parallelogram is by cutting it up and rearranging it into a more familiar shape. So you can see I just moved the green triangle to the right here, and what new shape do I get but a rectangle? And that leads us to the formula for the area of a parallelogram. So here I have the parallelogram we started with before I rearranged it, and then I went ahead and added this where I've moved the green triangle to the right. All I'm going to do is compare these two. Now, as you may recall, let me get my pointer here, the top length is the base. So we have the base is this whole distance here. It's also the same here. Opposite sides of parallelograms are congruent. And the height is this vertical distance right here. Now that it's rearranged, the base really hasn't changed, and the height hasn't changed. In the old days, back in elementary school, you would say the area of a rectangle is length times width. In 6th grade, we introduced another formula. We said base times height. And the reason we did that is because you also learn in 6th grade the formula for the area of a parallelogram, which is just the base times the height. Now we're going to take a look at the derivation for the formula of the area of a triangle. Here's my triangle. I just drew any old triangle, and I had the base laying flat here to keep this easier. And the main thing I need to know is the base and the height. And I know many of you have used this formula before, but where does it come from? Well, if I tried to slice this up, I wouldn't get very far because I'd have another triangle to find. And this is two different triangles. So there's actually a really cool thing we can do to make this easier. I'm going to make a copy of this triangle and rotate it like so. When I make the copy and put it on top, I create a very familiar shape, and I already know how to get the area for a parallelogram, and this will help me determine the area of a triangle. So using the formula for the area of a parallelogram, here's my height, and the base is this distance right here. So the total shaded area here will be just area equals base times height. But since this is two triangles, here's triangle 1, there's triangle 2, my answer will be 2 times too big. So this worked for a parallelogram, but now I need the area of a triangle. So what I'm going to do is say, take that base times that height and divide it by 2. And that gives you the formula that you've been using for several years now. We can also use the same approach to find the area of a trapezoid. So here's my trapezoid, and what I'm going to do is I'm going to make a copy, and I'm going to rotate it and line it up to create another familiar shape. So there it is. And I get the same effect as if I had rotated a triangle. Now I have a new parallelogram. And I can use this made of the two trapezoids to develop the area, the formula for the area of a trapezoid. Okay, so first of all, I'm going to go ahead and label my different bases. Base 1, base 2, right? And not my best handwriting. There's base 2, and there's base 1. And I still have my height, which is this vertical distance. If I'm looking at the whole parallelogram that I just created, you can see the height's the same, but now the distance across my base is actually base 1 plus base 2. So if I was finding the area, the entire shaded area, I would say base 1 plus base 2 That's my new base times my height. But I really don't want the area, the whole shaded area. I just want about half of the area. I want one of the trapezoids. So what I'm going to do is divide this by 2. And that gives you the formula. In 6th grade, you saw it written in this way. Now you tend to see a fractional 1/2 in front of base 1 plus base 2 times height. And there you have your formula for the area of a trapezoid. Finally, we're going to come to something completely different, and that is the area of a rhombus. Now, you're probably saying, well, a rhombus is just a parallelogram, and I can do base times height. And you would be absolutely right. But there is actually another way to find the area of a rhombus. So what I'm going to use are the diagonals of the rhombus. And to look at it a little more closely, I'm going to go ahead and pull 1/2 of the rhombus out so we can take a closer look at it and see how to get the area, the formula for the area of a rhombus. Now, let's go first and label the different sides that I have here. We have the 2 diagonals, and so I'm going to call this long one here diagonal 2. Diagonal 2. And the short one I'll call diagonal 1. Now, diagonal 1 is this whole distance from here to here, and diagonal 2 is the whole distance. Now, since this is a right angle here, this is also a right angle here. This is the height of my triangle, but it's not the whole of the diagonal 1, right? So it's just the half. So my height here is diagonal 1 divided by 2. Well, if I wanted to find the area of this triangle, the bottom part, I would say area equals base, which is diagonal 2, times the height, diagonal 1, all over 2. And then I have to multiply all that by 1/2. That's the same effect as dividing by 2. Well, the interesting part is if I'm trying to get the whole rhombus, before I've been cutting the area in half, but this only gave me half the rhombus. So I'm going to go ahead and multiply by 2 to get my total area. So these two 2's simplify. And so I get area equals diagonal 2 times diagonal 1, all divided by 2, or more like your formula chart, 1/2 times diagonal 1 times diagonal 2. So you can actually use the diagonals to find the area of a rhombus because one of the diagonals will be the base of the triangle and the other diagonal will be the height of both triangles put together. I should add one last thing here. I don't know if you noticed I just added the word or a kite. This formula also works for kites, and the reason is if you recall, the diagonals of kites are also perpendicular. And so they have this habit of cutting a kite into triangles with altitudes in them. So using the area equals 1/2 diagonal 1 times diagonal 2 will give you the area for a rhombus or a kite.